Section 2.9 talks about, is on page 155, talks about dimension and rank. And the idea is really simple if you really break it down. And let me get started with, suppose we have this set. Set B consists of P vectors. It forms a basis. So it is a basis for the subspace, for subspace H. That means those vectors are linearly independent. Right? That means the only solution, if you take C1 times B1 plus C2, so the only solution to this is C1 equals C2 equals C3 all the way equals C sub P equals 0. For each vector x in H, this vector will be a linear combination of those if they form bases. So basically what they're saying, if B1 through B sub P is a basis for the subspace of H, any vector in H must be a multiple of those with the following weights. And they call this vector, x sub P is called the coordinate vector of x relative to B. Fancy word. It has a lot of meaning in linear algebra, but we're almost at the merge of it. Or this is the B coordinate vector of x. If we were doing the applications, I would have emphasized that a lot, but since we're not doing applications, no point to really stress this out without you practicing. In 3 and 6, find the vector x is a subspace of H with bases. So these are bases. What does that mean? Bases are linearly independent vectors that span the space, and they satisfy the three conditions. Zero's in there. C times a multiple of that would be in there, or the other definition, C times one vector plus C times another is basically the commutator property of addition. Well, they're telling us these are the bases. This is a vector in there. Find the B coordinate. Well, it's simple. How is that? You're going to multiply this times C1 plus C2 and set it equal to that, or simply by now we are hopefully this comfortable. And if I do the magic, I will get that this x of B is actually the weights 5. I'm going to move this a bit to the left. I didn't even realize that was on the right. I could fit both of those. They're really simple if we've been keeping track of what is what and been paying attention and doing the homework and all of that. Same deal here. They say, look, here's those form bases, but here we have one exception. Those vectors are those vectors are 3 by 1. So if I work this out, I already know what's going to happen. And can you guess what's going to happen? One of those rows is going to zero out, and let me get that. So we know here that x, the coordinate vector, is actually -5 halves 1 half. Right? Again, we're looking at this, we're figuring, wait a minute, this is x1, x2. I really don't need 3 equations. I only need 2 equations. So they gave us an equation that wasn't needed. And there it is. Now, let's get those defined so we can play with them. And, oh. Okay. Here we go. The dimensions of a non-zero subspace H, denoted by the dimension of H, is the number of vectors in any basis for H. The dimensions of the zero subspace is defined as 0. No biggie. A bit hard to prove, but we're not going to worry about that. This part we want to worry about, and this part we want to really get out of the way. The rank of a matrix, denoted by the rank of A, is the dimensions of the column space. Do you remember that? If you remember pivots, And remember to take the original. That doesn't look like pivots. And remember that the non-pivots form the null space. So if I add the two, if I have n columns, it's always the columns that count. If I have n columns, then between the pivots and the non-pivots, they should add up to n. And if you remember, the dimension of the null space are the free variables. Not only are we gonna figure out what they are, we're gonna find them too. Display a matrix A and an echelon form. So they did the work. Again, something we're gonna do for you. We just want to make sure that you understand how this game is played, and you want to be careful not to rush and mix things up. Find a basis for the column of A and the null of A. Then state the dimensions of these subspaces. Well, look at that. That's 1, that's 1, and that's 1. So we already know that the column of A is actually defined by 1, 1, negative 2, 4, negative 2, negative 1, 0, 1, and the third one, that one, 5, 5, 1, 1. And if we really want to get the null space, the null of A, we need to solve this. For the null of A, I need to set A x equals 0. So basically, just tag zeros here and work them out. And we already know that we have x3 is free. And x5 is free. And x4 is x1, 2, 3, 4, 5. So x4 is 2x5, and x2 is 3x3 plus 7x5, and x1 is oh wait, I gotta work that one out. Okay, I should have reduced that further, but that's okay. x1 is gonna be 2x2 minus 9x3 plus x4. So again, if you don't reduce it, it's some work. Minus 4 you know what, I'm gonna copy it down. Let's just give me 1 sec. Okay. And how much is it? Recording? Okay, there it is. Oh boy. Alright, got it back. So if I reduce it more, that's what it looks like. So again, they're not gonna change. So I have x sub 5 is, and again, it's best probably to put those up there. This way you could start practicing how to do this. X sub 5 is free. X sub 4 is 2x sub 5. X sub 3 is free. X sub 2 equals 3x sub 3 plus 7x sub 5. And x sub 1 is negative 3x sub 3. So basically, if I wanted to write x, normally is written as x1, x2, x3, x4, and x5. So basically, you're going to write that as x3 times what? Negative 3, 3, 1, 0, 0, plus x4 times x5 times 0, 7, 0, 2, and 1. So basically, negative 3, 3, meaning any multiple of those will form basis for the null space, and any multiple of the above 3 vectors form basis for the column space. So again, given those, can you tell what it means? That's a big deal for us. Here's another one. If I did the row reduction, there it is. Well, again, I look for pivots. 1. So again, 1, 2, 3, 4, and 5. 2, 3. So, basis for the column of A are really simple. Take the original 1, 2, 3 vectors, 1, 5, 4, negative 2. Each of those is an R4. Right? That's the x1, x2, x3, x4. So don't mix dimensions with where you are. A vector in 3D is always a vector in 3D. How many vectors you have, that will be the dimensions of the column. So the dimensions of the column space is really 3 because there are 3 of them. But each of those vectors is an R4 because it has 4 components. Right? I, J, K, and one more. And now if I take this and I take it a step further, and again I'm going to cheat a bit. Basically multiply this by 4, add it to the top row, and so on and so forth. So this, no need to do anything about. This, no need to do anything about. But this one, here, let me copy it. So if I set AX equals 0, I will get this, and that means what? Again, X1, X3, X5. X1, X2, X3, X4, and X5. That means out of this, the last one was, so I noticed that X5 is free, X4 is 0, X3 is 0, because that's a 0, X2 is free, and X1 is negative 2X2, and X4 is 0. That's it. So we could say that X is actually X2 times 2, 1, 0, 0, 0, plus X3 times 0, 0, 0, 0, 1. If I'm not mistaken or don't make a mistake, basically the null of A would actually be 2, 1, 0, 0, 0, 2 vectors. So the dimensions of null of A is 2, and the dimensions for the column of A must be 3 by that definition. They must add up to the total, which is 5. And here, did I find it? No, I didn't. Dimensions of the column of A, that's actually 3. That makes this a 2. Alright. Let's see if you can get this part out of the way. It says, find the basis for the subspace spanned by the given vectors. What is the dimension of the subspace? Do you know what that means? Let's make sure we're getting this. Find the basis for the subspace spanned by the given vectors. What's the deal with bases? Bases must be linearly independent vectors. We already know that those are what? So what would you think? It's very hard to figure out how many of those are multiple of each other. So what you do, you write this. Okay, there we go. We write this as, and we're going to use raw echelon form to really figure out which of those are multiple of each other, and they're going to fade away. And what we're looking for to form bases are linearly independent vectors. If I do my magic and I get the following, so what do we notice? The first two, 1, -1, -2, 5, and 2, -3, -1, 6. Those form bases for the subspace. What are the dimensions? What's the dimensions of this? The dimension would be what? 2. Each of those vectors is not in R2. Don't mix R2. R2 simply mean X and Y. 2 of those entries. This is in R4. So the next problems are just going to check if you understand the theorem or how this works. Let me get them up and here are some couple of questions. It says, suppose you have a 4 by 7. Suppose you have a 4 by 7. Three pivots. Some pivots somewhere. Is the column of A R3? No. It's not. The dimensions of the column of A is 3. That's correct. But the columns of A are 4 dimensions. 1, 2, 3, 4. 4 dimensions. X, Y, Z, and K. What is the dimension of the null space? That's easy. Dimensions of the null of A is, if this is 3 pivots and we have 7 of those, so 7 minus 3, that would be 4. To find it, that's a lot of work. And to get number 20, let me see. Yeah, I'm gonna make some space as well. A bit of space. And again, a rough sketch. 4 by 5. 1, 2, 3, 4. Probably that's the best way to do it. Each of those vectors is in R4. And we have 1, 2, 3, 4, 5 of those. We have 5 variables. It says, what is the rank of a 4 by 5 whose null space is 3 dimension? Null space is 3-dimensional. So, if the dimension of the null of A is 3, what does that mean? They have 3 free, and we have out of 5. That means the dimensions, what is the rank? The rank is the dimensions of the column space, right? And that must be 2. So between the null space and, again, this theorem right here, what was it? Right there, that theorem. Rank of A plus the dimension of null space must equal n. So, this theorem, I'm not really using it here, but I use it a lot in differential equations. I'm going to refer back to it. And I did use it back when I taught linear algebra all by itself, a whole course. If you notice, it doesn't start at A because this theorem started on a previous section. And there's your homework. And that concludes this section.